All right, let's assume that we're interested in the population mean. Mu is equal to mu 0 versus mu is larger than mu 0. Okay? So as we discussed before, first of all, we'll have to fix the probability of making type 1 error. Okay? So the probability of making type 1 error. Equivalently is to say the probability of reject H0 when H0 is true. Right? When H0 is true, you reject HO. Equivalently is to say X bar is larger than C, right? C is the critical value, so which means X bar falls into the rejection region. Okay? Given that H0 is true. So in this case, H0 is true means mu is equal to mu 0. So I'll set this is equal to alpha. For example, I let alpha is equal to 5%. So how can I find this C? Okay, so if we just focus on, H0 itself, it will be like this. So this is your C, okay? So this value is your C. So this area is your alpha, right? We want this area to be 5%, and the rest of this area is equal to 95%. Okay? All right. So, like we did before, we can convert this X bar to a Z random variable. So Z is a standard normal random variable, right? Remember how did we construct Z given X bar? So we use X bar minus the expectation of X bar divided by the standard deviation of X bar, right? So in this case, X bar is equal to mu, and standard deviation of X bar is sigma divided by square root of n. So this one follows the standard normal distribution. Okay, so its curve will be like this. Now this is the Z curve. Okay, it's symmetric with respect to 0. And we have to find a cutoff value to make this area to be equal to alpha, and this area to be equal to 1 minus alpha, right? So we call this cutoff value as Z1 minus alpha, right? Okay, so it's pretty easy for us to find this cutoff value given the value of this alpha, right? So how can we do this? So the probability that X bar larger than C given mu is equal to mu 0 is equal to X bar minus mu divided by sigma divided by square root of n, larger than C minus mu divided by the same thing, given the condition that mu is equal to mu 0. Okay, so this is my Z. And this one, I'm going to call this a new stuff called C prime. So we have Z is larger than, or before that, we have the condition that mu is equal to mu 0, right? So mu is equal to mu 0, so you're gonna plug this one inside of it. Okay, so we have Z is larger than C prime is equal to alpha, right? Because we want to fix the probability of making type 1 error to be equal to alpha, which is 5%. Okay, so this C prime actually is this one, the critical value, Z1 minus alpha. So you can use the Z table to find this critical value. Once this critical value is known, all right, now mu 0 is known, okay, n is known. If you assume that the population standard deviation is also known, okay, so this is known, this is known, this is known, and this is known. So everything is known, which means you can have this C, okay? So this C is equal to this stuff, right? So this is how do you find the critical value, C, under this hypothesis, okay? And similarly, if your null hypothesis is mu is equal to mu 0 versus mu is smaller than mu 0. So equivalently, you need to find the rejection region as X bar is smaller than C. Okay, so I'll write a curve to let you know this. So this is the curve of x bar, and this is mu 0, okay? And this is what you want. So you want to find the critical value C here, all right? But use the same strategy as before, all right? So your rejection region is, so this is alpha, right? So alpha is smaller than C, given the condition that mu is equal to mu 0 is equal to 5%. Or to be more general, we can say alpha. Okay, you can say alpha. And then you convert this x bar into z, right? So C prime, so this is your C prime. Okay, once this alpha is fixed, so you can have this C prime using the z table, right? And then because this one is known, this one is known, this one is also known, so you can have the corresponding value for C. All right, so we can have a general look at this one. Okay, so in general, a rejection region is the set of all test statistic values for which H0 will be rejected. For different hypothesis tests, the directions of rejection region varies. Okay, so in the previous example, we discussed mu as the parameter of interest. So in general, we're going to discuss the parameter of interest as theta, and the corresponding the corresponding point estimator or sample statistic as theta hat. Okay, if you assume that your null hypothesis is theta is equal to theta 0, but your alternative hypothesis is theta is larger than theta 0, so your rejection region is theta hat is larger than C. Okay, you have to find this C. And how to find it? First of all, you convert this theta hat into a Z distribution or Z random variable at this stage. Okay, like later, we're going to discuss more examples using T or some other distributions. But here, you just need to know, okay, I'm going to convert this theta hat to Z. All right? And also, if your alternative hypothesis is theta is smaller than theta 0, so your rejection region is theta hat is smaller than C. Okay? So this direction is the same as the alternative hypothesis. You see what I'm saying? Okay, so what if your alternative hypothesis is theta is not equal to theta 0? So your rejection region is equal to this. Okay, so namely, we call the first two tests as one-tailed test. And we call the last one as two-tailed test. Okay, for the first one, we like to find this C here, okay? And this is the alpha. So it's a right tail. It's a right tail test. And for the second one, we like to find the critical value here. And for the third one, we need to find the critical values for both sides. So it's called a two-tailed test. Okay? All right. So let's have a very specific example. So example 10.1. Okay, recall example 8.5. So if you do not have the corresponding slides, I will upload the slide on Canvas so that you could double check. Okay, so actually this example says the proportion of people who have the Wi-Fi service at home, and we consider the following situation. Assume AT&T's history records show the proportion P was 0.45 in 2016. And in order to know whether there is an increasing demand this year, they randomly selected 100 people and find there are 50 people have the service at home. So the sample proportion is 0.55. So based on this single sample proportion we observed, could we infer that there is an increasing demand this year? Okay, so in 2016, we have the proportion P is equal to 45%. And then we'd like to study whether there is an increasing, right? recently. So we draw a sample, and the sample size is 100. So among them, 55 people have the service. So the sample proportion is 0.55. So how can we set up our hypothesis? Okay, like I said before, we're interested in the population parameter. Here is the population proportion P. Okay, and we always set up, in the null hypothesis, we always set the parameter of interest is equal to something. Okay, I'll say this is equal to P0 versus the alternative hypothesis is we like to study whether there is an increasing demand. So I'm going to say P is larger than P0 on the alternative hypothesis. Okay, because in 2016, we know that the proportion was 45%. So I'm going to set up this as the reference. So this is 0.45. Okay, and this is what we observed from the sample recently. So we're going to use this p hat to prove evidence, to find the evidence either to support H0 or HA. Okay, so which means this is a one-tailed test. Okay, all right. Like we discussed before, in the second step, we need to specify the test statistic and the model. So what is the test statistic? So, because we know that p hat is equal to x1 plus x2 until xn divided by n, right? So each xi is a Bernoulli random variable, is equal to either 0 or 1. So 0 means this person does not have this service at all, but 1 means this person has this service. Okay, so the numerator actually is the summation of a bunch of Bernoulli random variables, so which is binomial. Okay, so we have p hat. We can use the property of x bar to apply to p hat, right? So p hat approximately follows a normal distribution when the sample size is large, right? So we can have the expectation of p hat is equal to 1 divided by n, the expectation of x1 plus x2 until xn, which is equal to np, so which is p. Okay, so the expectation is p. So what about the variance? So the variance is equal to, I believe all of you have done this before, so I'll just show you the final answer. Okay, so this is equal to p np by 1 minus p. Okay, so cancel one of the n's, so which is p by 1 minus p divided by n. Okay, so that's the sampling distribution of our sample statistic, p hat. Okay, so this is my test statistic. All right, so in the third step, find the rejection region. So this is the second step, our test statistic. Okay, so in step 3, find the rejection region. Like we discussed before, our alternative hypothesis is p is larger than p0. So which means our corresponding rejection region should be p hat is larger than c. Okay, so my rejection region should be p hat is larger than c. Okay, if you'd like to have a look at the corresponding graph, it will be like this. Okay, so this is p0, all right, and this is your c. So when p hat is larger than c, this is your rejection region. Okay, and we like to fix the probability of making type 1 error to be a very small number, say alpha. Okay, so we're gonna say the rejection region, right? Or we can just write p hat is larger than c, which means you reject the null hypothesis, given the condition that the null hypothesis is true. So p is equal to p0, right? And this is equal to alpha. Say if I set alpha is equal to 5%. Okay, so it's going to be p given p hat is larger than c, given the condition that p is equal to 0.45 is equal to 5%. In order to find it, we have to convert my p hat into a z random variable, right? Because we know that my p hat follows this distribution, okay? So I'm going to minus the expectation of p hat and divided by the standard deviation of p hat, okay? So this is my z actually. So c minus the expectation and the standard deviation, given the condition that p is equal to 0.45. And the corresponding probability is equal to 5%. Okay, so this is my z, right? This is my z. It's larger than, this is my c prime. Okay, but to be more specific, this c prime should be equal to c minus the expectation divided by the standard deviation. This is the variance, so you need to take the square root of it. Okay, so minus p divided by square root of p by 1 minus p divided by n. Okay, but we also have a condition that p is equal to p0, which is 0.45%. 0.45, right? So you have to plug this value inside of it. So this stuff is equal to 5%. So this is my c prime. Okay, now I have z larger than c prime is equal to 5%. Okay, so from the graph, you can see, so it's symmetric with respect to 0. And this is my c prime. Okay, so this c prime actually is just z 1 minus alpha. Okay, alpha is equal to 0.5, so you're going to find the corresponding value of z 1 minus alpha using the z table. Okay, then the c can be confirmed. Once the c has been confirmed, you can have the corresponding value for, once the c prime is confirmed, so you can have the corresponding value for c. Okay? Okay, once the c prime is confirmed, we can find the value of c. Okay, because the c prime is just z 1 minus alpha here. Okay, so if my alpha is equal to 5, so z1 minus alpha, you can check the z table, is equal to 0.65 approximately. Okay, so my c prime is equal to c minus 0.45 divided by 0.45 by 1 minus 0.45 divided by 100 actually, right? So the sample size is 100. All right, so this stuff is equal to 1.65. So we can calculate the corresponding value of c. So we can have c is equal to 0.53. All right, and then you can make your decision based on this, right? So you have p hat and you have f p hat, right? So this is p0, which is equal to 0.45, and this is your critical value c, which is equal to 0.53 here. Okay, you want to make this this area to be 5%, and the observed sample statistic p hat is equal to 0.55. Okay, so p hat is here, 0.55. So it falls into the rejection region. All right, once your observed sample statistic falls into the rejection region, we're going to reject the null hypothesis, okay, and support the alternative hypothesis, which means there is an increasing demand. All right, okay, so what if my c is not equal to 0.53, but here definitely is equal to this one? For the sake of this problem, I'm going to set the c is equal to 0.6. Okay, so this is equal to 0.6. So my observed sample proportion is equal to 0.55. Okay, so it does not fall into this specific interval. So in this case, I'm going to say I fail to reject the null hypothesis. Okay, which means there is no enough evidence to show that there is an increasing demand for this service. All right, but in this case, our C is calculated as 0.53, so which means my p hat falls into this interval. Okay, and we have to reject the null hypothesis.